take you to the practice quiz. So number 1, this is back in Calculus 1. The limit as x approaches a of f of x equals L if, so you're defining what the limit means. And let me give you 30 seconds more. So informally, what it means is, as x gets really close to a, f of x has to get really close to L. That's the idea. But we make that a bit more precise by putting it this way. If we can make f of x as close as we like to L by taking x to be sufficiently close to a on either side of a, but not equal to a. You're not allowed to reach your destination. You can have the function be undefined at a and still have a limit there. Like for instance, if there was an open circle right here, the limit could still be L. So, give me a little feedback on number 1. And if I was in your shoes, this would seem to make sense to me, but I would have had a hard time coming up with it. Okay, even the informal part, I think I would have had a hard time coming up with that idea. Okay, and how about continuity? From Calculus 1, f of x is continuous at x equal a if, and complete it. And 30 seconds more. Okay, so on this one, it's if the limit as x approaches a of f of x is equal to f of a. And when we teach this in Calculus 1, we say that although that's the definition of being continuous, the super informal definition is you don't have to lift your pencil as you come across a. But this implies three things. You can't have these things equal each other if the limit doesn't exist. Now, for this limit to exist, that means the limit from the left and the limit from the right both had to equal the same thing. And not be infinity, either one be infinity or negative infinity. And f of a has to exist. So if there was like a whole discontinuity directly above this and no other dot anywhere, then f of a wouldn't have existed. And then 3, that these two things are equal to each other. And give me a little feedback. Did you remember this? Could you reconstruct it? Any part of it? So, we're doing 2 sections today. This first section, limits and continuity, is going to be really quick. But before I get into that, are there questions? Any of the homework problems or anything else?
Yes, I do have the one homework question, please.
Okay.
Yes, it's in the on page 901. Number 31.
Page 901. 31. Let's get some space in here.
Yes, and my question is, it seems...
use the calculator to approximate the length of the curve, simplify it as much as possible before finding an approximation. Alright, so...
Yeah, the question was, I tried it, I'm sorry.
Is the length of the curve equals the integral of the magnitude of r prime dt from -2 to 2. And so the idea is, it's easier to remember than when Calculus 1. That formula for arc length was kind of tricky and not so straightforward to remember. It's only dependent on the speed. All you have to do is take the speed. And so we are going to say if this is r prime is, take the derivative of t and you get 1. 4t squared, it's 8t. 10, derivative of 10 is 0. So the magnitude of r prime of t is the square root of the sum of these things squared. We get this. And so this is going to be this integral. I'm going to write it like this. And then this one, it's not an easy integral. It looks like it shouldn't be too bad, but if it had a t dt, it would be fairly easy. It doesn't have a t dt, and it says use a calculator to approximate the length. So what it wants you to do at this point then is to substitute this into like a computer or calculator to figure this out. Now, if this was odd power, an odd root, we could check to see if symmetries, would give us 0 on this, but it's not. So, but we could, because it's even powers, we could say it's double from 0 to 2, but that's not really any savings in time. So I would take something like this, 1 plus 6, and I would just put it into something like Wolfram alpha, and let's say integral from -2 to 2 of, and let me go back to that, 1 plus 64 x squared to the 1/2. Raised to the 0.5. And that looks like what I was intending, and I'm going to get this at about 32.5, and that would be my answer. And the picture looks like this, and like I said, you could have done double the integral from 0 to 2 because of the symmetries involved. Isu, does that answer your question?
Yes, my question part was in the integration. Is a square root 1 plus 64t squared there? This part. And as I look at the back, yes, can you hear me? Hello?
Okay, if no more questions, let's go to 15.2. Limits?
I think Haisu, or I don't think you can hear Haisu.
He must be your enemies.
I don't think he can.
Maybe he like turned his audio off.
Definition of being continuous.
The volume?
Now we ask, how are these definitions of limit and continuity different in 3-space or in even higher spaces? So, this limit as xy approaches a point AB of this function. This is because now, remember in chapter 15, we're always in 3-space functions, generally speaking. Sometimes we're in higher space, but it's generally we're looking at functions like this, which we call surfaces. Okay, and so the domain is the xy plane or the floor, And the limits would now look like this. The definition for the limit in 3 space stays essentially the same. But here's the thing that changes. We can approach AB from an infinite number of directions. So, if I have A, B, so my X and Y axis, I'm approaching this point. I might be approaching this point. See, if I was approaching A along the X-axis, there's only 2 ways I can do it. From larger than it and from smaller than it. But if I'm approaching the point AB in the XY plane, now notice I didn't draw this 3 space thing. I'm extracting out the X and the Y and putting it in familiar, because here's the domain. We can approach AB in the domain from this direction, from this direction, from this direction. We have an infinite number of ways that we could approach a point. So we're going to try to keep this definition the same as possible that we had before, but we have to take this into account, that now you can approach this through all kinds of different ways. Let's look at what happens in this case right here. F of xy is this funny looking function. Let's find the limit as xy approaches 0, 0. Now, I mean, it looks kind of too long. It looked better in this next one. This was able to go underneath it. The limit as xy approaches 0, 0. 2 ways that we can do it. One is along the x-axis. There's other ways we could do it as well, but we're just looking at these 2 ways. And now we're going to get the same limit if we approach the point 0, 0 from either direction. All right. Now, when I'm going to do this, let's just remind real quick. If it was an easier problem, the limit as x, y approaches the point 2, 4 of this function, all I do is plug in the values. When x is 2 and y is 4. To find any limit, you just plug in those values and see what you get. But on this one, when you plug in 0, 0, you're going to get 0 on the top and 0 on the bottom. Does anybody remember the name that we used for this case? When we plug it in and you get 0 over 0? Anybody remember that name?
L'Hopital's rule?
Indeterminate?
The form is 0 over 0 when you plug it in. So it doesn't resolve, can't determine what your answer is. So we call it the indeterminate.
I don't think he can hear any of us
Only
talking.
one where we couldn't determine the answer until we do some simplification or some kind of algebra to get this down. All right. So if we approach along the x-axis, so we're approaching along here. We're approaching this point. Along here. Getting closer and closer to this. Does anybody have any suggestions how I might find this? If I'm on the x-axis, do I know something about either one of these variables, x or y? One, two. If I'm at this point, my coordinates are 2, 0. I'm at this point, my coordinates are 1, 0. I'm at this point, my coordinates are 3, 0. If I'm on the x-axis, what do I know about either x or y? Anybody? Now I'm wondering if I can hear you all, and if we've maybe lost connection. Can somebody speak to me and let me know?
3.141592654.
I can hear you, Cameron. All right, y'all can hear me okay?
We never
can you
lost
hear me?
you.
Can you hear me?
Yes, I can hear you. All right. Everything's all right. So we're good? All right. If we're approaching 0, 0 along the x-axis, what must be true is y is 0. The y coordinate is 0. Just like here, all these points where the x is getting smaller and smaller, but the y is staying 0 all the time. And so this limit is equal to the same as the limit as xy approaches 0, 0. Let's just plug in 0 for these, and you get x squared over x squared. And although x is getting smaller and smaller, you're getting the same thing, both top and bottom. This is just 1. Is this making sense?
Yes.
All right, we're good with that. All right, so let's do it again now down here. As xy approaches 0, 0 along the y-axis, we have these values, which is maybe 0, 1, 0, 2, 0, 3, and what must be true here is that the x is equal to 0. And so this is the same as the limit as xy approaches 0, 0. And zero out these. And you will get a negative 1 over here. So the limit as xy approaches 0, 0. For most situations, it's going to be super simple. You just plug it in. But the ones where we'll really be interested in are the ones that are the indeterminate forms. Just like we were in Calculus 1, because the derivative itself was a fraction that turned out to be an indeterminate form. And when you do this, you can get two different values. So what would we say that the entire limit is?
Indeterminate?
Oh, I'm sorry. Limit does not exist.
Not yet.
Okay, yes. Thus,
I
the
agree.
limit as xy approaches 0, 0 of f of xy does not exist. Just like for a limit to exist in two space, the left-hand limit and the right-hand limit had to be the same. Now it gets more complicated. Every single limit has to give you the same answer for the limit to exist. And you can approach it from an infinite number of directions. But it's got to give you the same thing no matter what direction you approach that point from. Now if we were approaching a point like 2, 4 up here, that in every single direction you're always going to get this result. But some of these could be strange, and we could wind up getting a limit that does not exist here. Alright, and let me show you a quick picture of this. So let me go to my document camera here. Alright, here is an image of this graph, and it's a nice surface except around the origin. And notice one of these, like this might be the, because which one, let's look at them real quick. Along the y-axis it was lower one. Coming along the x-axis, it was higher. Okay, so this one must be the x-axis. As you approach along the x-axis, now this is like a torn sheet of paper. If we were in the physical classroom, I'd make a little slit in a piece of paper, and I'd carefully maneuver my paper so it had this kind of thing happening. And then you put these boundaries infinitely close to each other. They look like there's a nice big gap. And then there's another gap down here coming along this axis. And this is the y-axis along here, and here's the x-axis along here. And this, you kind of force the papers together like this, and you get this crazy thing happening. And so you might have some special cases like this where a limit doesn't exist. And let's just put this into here. Oops, I didn't give it enough space. And I could shrink it down a little bit too. Alright. And let's go to continuity. And being continuous in 3 space is the same as it is defined in 2 space. And this is right from the textbook. Function f is continuous at the point AB on the floor, in the xy plane, provided that, now they could have just said the limit is equal to, just like we did over here. And we could have said the limit equals this, but they instead wrote the three different things that applies. So these three things all are a part of the limit as x, y approaches a, b of f of x, y equals f of a, b. In order for this to be true, f has to be defined, and the limit exists, and they have to equal each other. And that finishes up the 15.2, limits and continuity. Any questions before we move on to the main section for today? Alright, let's go to the main section, partial derivatives. There's just one practice quiz problem. State the definition of the derivative in two space from calculus 1. Let me give you a minute there.
You want us to type in?
No, just go ahead and write it down on your own paper. And let me give you just a few more seconds and then I'll write it up here. Okay, so in calculus 1, f prime of x is defined to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And I'd be curious, were you able to remember this? I'm not sure that I would be able to remember this between my Calculus 1 and 2s and 3s classes when I was taking it. So give me a little feedback on that. I probably wouldn't have, and that's one of the reasons why I ask these questions a lot. Oh, yes, thank you. The hand cam does cause some extra noise. Okay, and all right, so what we're going to do is we're going to try to extend this ordinary derivative into 3 space. And you would think, all right, this is not going to be any problem. We can take the same definition, throw it into 3 space, but it turns out, no. And in fact, when you're in 3 space, we don't use the term derivative anymore. There's no derivative of a 3 space function. There is partial derivatives of a 3 space function. And the closest thing we're going to get to what we call a total derivative is something that we're going to call a gradient, and that'll have a very specialized meaning. But we're going to have partial derivatives instead of derivatives. So this is a pretty important section, one of the most important sections we're going to be doing in Calculus 3, because it's, Calculus 3 is pretty much taking calculus into 3 space. And the most important concept in calculus is the derivative, but when you take it to 3 space, you don't have the derivative. You have partial derivatives. Okay. So, we're going to start with this table. In the table below, from the National Weather Service, the heat index, I. And now this was created sometime way back, kind of like what it actually feels like when it's hot outside. I used to live in Houston. I lived there for 15 years. I lived in Houston for 15 years, and the temperature would rarely get above 90 degrees. But when, during the summer, it was generally 90 degrees all the time, and then at nighttime, it didn't cool down one iota. It was exactly as hot all night as it was, and the 90 degrees there felt suffocating because so much humidity was in the air. Most people, like people who get transferred to Houston for a year, they generally get hazard pay because they're going to a place where it's so uncomfortable. And people would treat the summer in Houston kind of like people treat the winter in super cold places, which is, they'd hardly ever go outside. If you didn't have air conditioning, you were really uncomfortable. So when you put the heat, the temperature and the humidity together, you get something that kind of like gives you a better picture of how intolerable it is. And this is the heat index. The heat index of what the temperature feels like to a human body when the relative humidity is combined with the air temperature. Okay. And so the this portions, let me just show you. The table is supposed to look like this, and actually I can get it to look like that. Let me do that. Let me get over here and delete this. Let me do this one more time here and try to do a cut instead of just... I'll just go underneath this and insert some space. So let's take this table and do better inserting it in here. Alright, so for instance, if the temperature is 90 degrees, but it's only 55% humidity, it doesn't feel so bad. It feels like it's 98 degrees. If the temperature is 90 degrees and it's 85% humidity, it feels as bad as if it's 115 degrees. Alright, now there's one special one that we're going to be looking at, and that's highlighted. When its temperature is 96 degrees and the relative humidity is 70%. Now, if you had the temperature at 96 degrees, but the relative humidity was 65%, it feels like 121 degrees. And then by increasing by 5 percentage points, you jump to, it feels like 125. You jump by 5 percentage points, it feels like 130 degrees. Similarly, we could look down this column. When it's 70% humidity, the temperature is 94 degrees, it feels like 118. If it's 96 degrees, it feels like 125. If it's 98 degrees, it feels like 133. Okay. So the first question is, when the temperature is 96 degrees and the humidity is 70%, so we're at this grade area right there, 125, which has a bigger influence on the heat index I? A 1 degree increase in temperature or a 1% increase in humidity? So figure that out on your own, but when you get your answer, type it into your group chat. But don't hit enter yet. I'll tell you when to hit enter. Go ahead and hit enter and discuss this in your group chats. Okay, group one, any insights you can pass along to us here?
Yeah, I'm pretty sure that temperature has a bigger effect because if you look at so for humidity, if we go up by 5% humidity, we go up by 5 in I. So you could say that humidity, 1% humidity adds 1 to I. But temperature, if you go up by 2, it adds 8. So that increases by 4 for every 1 degree.
Ah, okay. So what you were doing is you were focusing here to here. And you said, when H goes up by 5, the I goes up by 5. Okay? Increase H by 5. I goes up by 5. And then you looked this way, from here to here, increase T by 2, I goes up by 8. And how do we summarize these two findings? Should I go 5, 5, 2, 8, or should I combine it into like one number for each?
I would say that you should normalize H and T so that they're 1. So like it's like, I guess it would be like the partial derivative of I with respect to H.
Ah,
So yeah.
good anticipation. All right, so we're gonna, let's call this a slope, but we're kind of changing just T. And it's the change in I, because that's the output, over the change in T, 8 over 2, which is 4. And this other one is a slope, but it's with respect to H. And it's the change in the output versus the change in the input H, which is 5 over 5, which is 1. And what we see is 4 times the sensitivity to temperature than there is to humidity over here. So it goes up a lot bigger. Now, did anybody do it differently than just looking from this to this number and from this to this number? Anybody?
No. Are you suggesting that there is another way to do it?
Yes. Yes. This was an excellent way to do it, but it wasn't quite fair. It's kind of looking and giving more weight to after 70 than before 70. And they really should be given equal weight. So this circle over here, let's take my eraser. If we went from here to here, we would not be favoring the after more than the before. And that's going from, let's erase up here, that's going from here to here. And so this, now that's changing the humidity, the slope when you're doing humidity. Is change in I over the change in H. And I changes by 9, while the H was going up by 10. So it gives us almost the same thing, 0.9. And the green, notice you don't even use this piece of data. What the actual I is at 96 degrees and 70%, you never even use. You do it more accurately like this. And as you go from here to here, you'd be going over here, from here to here. And it's a slope focusing on the temperature change. Change in I over the change in temperature, which now the I increases from 18 to 33, which is 15, while we went 4 degrees, and this is very close, 3.75. And then the ratio 3.75 to 0.9 is really close to 4. But we get really close. But so which has a bigger influence on I? It's the increase in the temperature. 4 times as much as the increase in the humidity.
So
Yes.
how are we supposed to know that we are supposed to look quote unquote before 70% in order to come up with the correct value of I
Um,
from this question? Because this
oh,
question does not mention anything about looking at humidity and temperature at 65% humidity or 94 degrees Fahrenheit respectively.
I think you make a very good point, because we'd have to see how this is worded. When the temperature is 96 degrees and humidity is 70%, then we're only going to be going forward in time. Or forward in, hold on, no, it's the word increase. Since if I'd have said, which has a bigger influence on I? A change in temperature 1 degrees or a change in humidity 1%, then we'd have done it the way that I did it, and we'd have gotten this answer. But when we say a 1 degree increase in temperature from 70 towards 75, then you're right. We should actually be using this method over here. So the way it's worded would tell us, this would be slightly better than this. Good point, Cameron. And all right, now I want to talk about how we do this. And Rowan was stating this in terms of partial derivatives. And that's exactly how we're going to do this for here. So let me restate what we've done. But so we're going to look at temperature. Now I was doing temperature in green, so I'm going to stay in green. When we're focus on the effect of changing the temperature. If you're going to do this, how do you do this? You hold the humidity constant at 70%. All right. Now, holding the other one constant is vital to this, to see what happens when you increase the other one. All right. It's like we're creating a new function. We'll call it G. Of T. Now, we have kind of an I of T for the index, I of T and H. G of T is going to equal the same as I of cap T, comma, 70. If you're used to thinking of functions with small letters, it's kind of like this. G of T equals F of T, comma, 70. Where F would be the I function. but we could also be using the letters like this. And in general, when we're using G and F to get it in really comfortable letters, we might think of X and Y. Where X is the temperature and the Y is being held constant. Y is the humidity level. Now, when we're finding the effect of temperature, we are holding the humidity constant and we're making sure that we stay in this one column. And then we find, let me get a little more space here. We find G prime of cap T. And we'd find G prime at a specific value of T, which is 96. G prime of 96 is approximately the change in just what we were doing over here, change in I over the change in T. And if we did it this way, 8 over 2, which is 4. Okay. Now, when we get using this kind of notation, we wind up going to something like this. F, and we put an X under here. And we would say and this right here we say it's the partial derivative. We often leave out the word derivative. Partial of f with respect to x. The partial of f with respect to x. And over here, g was just a function of one variable. So it's just an ordinary derivative for cap g. But the real function I was a function of two variables. And it doesn't have a prime. You can't go I prime. Because you're saying, because remember what is the definition of the derivative? Well, the interpretation we often used was it's a change in the output every time the input increases by 1, provided we stay in the tangent line. Well, which input increases by 1? You have to specify. And so that's the problem with having an I prime. You can have an I sub t at 96, 70, and that's approximately 4. But we're going to be using this kind of notation with little f's and little g's and x and y's, and commonly we'll see it as partial f with respect to x. And similarly, we'll get the partial of f. Now if we go to blue, the partial of f with respect to y at 96. 70. Now that's the blue part, and that was approximately 1. And that could have been written in terms of I, with respect to humidity, evaluated at this particular point. We can't find the function in general because all we had was table values. We can only find it at points. Was approximately 1. But we're getting the idea now of why it doesn't have a total derivative. It just has partial derivatives. Because you've got to hold one thing constant and then say, well, what's the effect of a 1 unit increase on this variable? And then reverse it, hold the other variable constant. What's the effect of increasing the other one by 1? And then you get the partial derivatives. Any questions? All right, let's take a break here. We will start again. At 6:46 p.m. And does anybody need to speak to me before I take my break?
Yeah, just quick question, please.
Yes.
We missed the communication tool before, so just go back to the first question that I asked. What I wanted to ask about when you integral about the RT, the T, the arc length problem. My question was integral the square root 1 plus 64 t squared dt. Is I found at the back of the book, the square root, in general, the formula says integral square root of a squared plus x squared dx. It will be x over 2 square root a squared plus x squared plus.
All right. What rule number was that in the back of the book?
It's on the page. Let me see. It's on the page 76.
Page 76?
Oh, I'm sorry, it's just not 70. It's the back of where the table of integrals at the back of the book after the index of application and index after all that.
And it's rule number 76?
Yes, integrals involving a squared plus x squared.
Okay. Now,
Yes.
all right. The problem with using that rule, this is rule 76. Oh, hold it. No, that's got the square root. That's got the, yeah, okay, no, this is good.
Right. So I got completely different answer from the book answer, which is 32 point something.
32?
No, I got 258.
All right, let me, I'll do it this way with that rule when we come back from break, okay?
Okay, I just did the hand calculation, not with the technology. So that's why maybe I said.
All right, so yeah, so there was a problem for a little while, huh? Where we couldn't communicate back and forth.
Right.
Were you having trouble hearing me as well during that time?
No, not right now. No.
Okay, gotcha. But during that time though, there was a problem.
Yes.
Okay, got it. Okay.
Right.
Yeah,
Thank you.
we'll look at this after the break.
Thank you.
You're welcome. All right, so we shall begin again here, and let's do this integral with this formula and see if we get 32.5. All right, so we're going to have to set let x equal 8t. That's how the x squared is going to be 64t squared. And so dx 8 dt, and so this integral would be the integral of 1 plus x squared. This would be square root of that. 1 plus x squared, and then the dt is 1/8 dx, like this. And when this is t equals -2, and if you put in t equals -2, you get x is -16. And t equals +2, you get to +16. And then rule 76 says this is, it's kind of long. It says it's going to be equal to, now the 1/8 will go out in front, and it's going to be x over 2, and the a is 1, so it's going to be then the square root from rule 76, a squared, which is 1 squared, so 1 plus x squared, plus a squared over 2, which is 1/2 ln of x plus square root of 1 plus x squared. And then it says plus a c, but instead of plus a c, we have it from -16 to 16.
Oh, I see the difference, Robert, right now. So what I did, it was just plugged in the number. So it wasn't just x over 2, it becomes xt over 2. So that's why I didn't pull out 1/8 in front of the bracket.
Okay.
Right? So if a 258 divided by 8 is a 32, so I guess that's where I missed. I just plug in all the numbers without
Great.
derivative. Okay, I see the.
It's this 64 that doesn't fit into the rule, so we had to do a u substitution to get that.
Right, yeah.
Okay.
Okay,
Right.
I see.
So I'll just
Thank
put
you very
dot from here.
Yeah.
Okay. Well, I'm glad you asked about that and got that cleared up. And let's go back to partial derivatives. All right, and all right, we're over here. So we had set up the first partials. Okay. And we'll come back to this part. Here's some interesting visualizations about partial derivatives. But let me jump over to the definition of partial derivatives. All right, look at how this definition, let me place it next to our definition in two space. Let's move this over here. All right, so comparing these two definitions over here, there's only one input variable, and then you can put the prime. When there's more than one, the prime doesn't make sense anymore. More than one input variable, because it's which variable are you talking about? How sensitive? If you want to talk about what happens when both are changing, we'll eventually be getting to that, and that's going to be a gradient, and it's kind of, you know, it's about as close as we can get to just the regular old derivative. All right, and this was, now this could have been, instead of AB, if they had put XY, it would look more similar to this. But those are they're treated as variables, A and B, in this definition in the textbook. Okay, and so it's the same kind of thing. It's just you're holding the B constant. That's not changing, and you're just changing the X. And then vice versa down here. You're holding the X constant here to here, and then you're only changing the Y with that H. So we kept the definition as much similar as we could, but we had to go one at a time and hold the other one constant. Alright, so now when you compute partial derivatives, it's really interesting how you've got to do it. Find the first partial derivatives. We're going to find fx. The partial derivative with respect to x. When we're doing this, we have to hold the y constant. Now, when you hold the y constant, you see this view it more like this. For this viewpoint. The y cubed is just like the 4. It's just gonna, and you treat it as if it were a constant. And so this part, the 4y cubed, just stays out front, and you just take the derivative of the x squared, and that's going to give you 2 times x. And then, so we did that with the first term. Now we go to the next term. And we think of this next term as minus 2y to the 4th as the constant out front times x. And the derivative of a constant times x is just the constant. So fx, reduce that a little bit, 8xy cubed minus 2y to the 4th. It becomes really easy computations to take these partial derivatives after you get used to this. You get used to treating the other variables just like it was the number 5 or something. Okay. So, you try fy. And when you get your answer for fy, type it into your group chat. and see if you're agreeing with your partners. And type it in, but don't hit enter yet. Okay, go ahead and type it in, or hit enter. And group 2, what are you getting for the partial with respect to y?
So I got 12x squared y squared minus 8xy cubed.
Okay, so you come back to here, you treat all this as if it's a constant. This 3 gets multiplied in, and it becomes 12x squared y squared minus, and then you treat both of these as if they're constants now. 4, and you got what, 8x y cubed, like this?
Yeah.
Okay. All right. So we did the first part. We found the first partial derivatives. Now it says, then find the 4, I should have left out a word, second partial derivatives. Now, what does it mean, the 4 second partials? Well, just like you can take y prime, y double prime, you could take extra partials. For instance, you can take fx x. And fxx means the partial twice of f with respect to x. So you just do this one again. So let me give you a moment. Get fxx and get fyy. Alright, so I'm going to take the partial with respect to x of this, and the 8y cubed is just the constant out in front. That's all I get here. And then this is just a constant, it becomes 0. So 8y cubed, that's all it is. And then fyy, treat all this as a constant. 2 times that is 24 x squared y. Take this 3, multiply it in, minus 24x y squared. Alright, any questions? Alright, now, it says find 4 second partials. We only found 2. The other partials are when you do 1x and 1y. Before we do that, though, let's look at this theorem. The theorem says that the 2 mixed partials will always be equal to one another. As long as you're having continuous functions that you're working with. And let's check that theorem out. Now, when I do this, I always get confused. And I think, alright, does this mean I do the partial with respect to x first and then the partial respect to y, or do I do the partial respect to y first and then the partial respect to x? Well, it turns out that it doesn't matter because either way I'm going to get the same thing. I think, if I'm remembering correctly, you take this one first and then this one. So let's take the partial respect to y. What it really means is, now, oh, by the way, let me introduce this notation. Fx is also this. Partial of f with respect to x. When you see the regular derivative, it's a d, df, dx. When you see the delta, the Greek sigma, the Greek symbol delta, that means partial derivative. It means f is a function of more than one variable, and you're taking the partial derivative with respect to that variable. Okay, and so if this one was taking the partial of, let me get to my eraser here for a second. This might mean the partial with respect to x of fy. I think it means in that order. But then again, if I remembered it wrong, it doesn't matter. Because as long as I'm consistent between these two, I'll do one way and the other way. So I've already taken the partial respect to y and I've gotten this. Now I take the partial of this with respect to x. And I come back over here and I'm going to get 24 xy squared. And to take the partial of this with respect to x, I'll just get the minus 8y cubed. And this might mean the partial with respect to y of fx. So you're doing one of each. And if I've done the fx first, now the partial respect to y, this times this is going to be 24 xy squared. Oh, it's matching up. And then the partial respect to y of this is minus 8y cubed. Kind of like magic. It'll always turn out to be the same. The mixed partials are always going to be equal to one another. All right, give me a little feedback. How do you feel on this? Holding one constant, doing the other, do you need a lot more practice, or does it seem pretty natural? Okay. All right, let's take one that's more complicated. This is actually in 5 space. There's 4 input variables, and then the 5th variable is the output of this. And find the first partials. So let me give you a minute with this. So we'll all do them, in alphabetical order. Do the F, W first. Okay, so the FW, we're going to hold this part. It doesn't have any W's in it. So you might just write that down first if you want to. Constant times a function, derivative of constant times a function is a constant times the derivative of the function. Now we need to take the derivative of the cosine of something that has the variable inside it. The derivative of cosine of something is negative sine of that something. And then you have to use the chain rule times the derivative of the internal, but the derivative of w plus x is just 1. Derivative of w with respect to w is 1 plus 0. And so this turns out to be negative sine, I can put them in this order, w plus x and 1 minus 8, like this. Alright, do f of x next. And keep on going if you've already done with it. Okay, so then this part is going to be constant again. Derivative of this with respect to x, the derivative of sine of something is, or cosine of something is negative sine of that thing. And then times the derivative of the internal, which is just 1. And put w plus x first. F y and f z. I'll do both those together in just a minute. I'll give you a minute in case you need a little more time with those. Alright, so the fy, this part is going to be the constant, there's no y's in it. The derivative of sine of something is the cosine of that something, times the derivative of the internal, which is, with respect to y, is just 1. So that's it. And fz is, and this part's a constant, so it's the cosine of that, and then the derivative of sine of something is the cosine of that something, times the derivative of the internal, which is now a negative 1. So that negative sign might go out in front, and then this would be the result here. So let's more practice on getting the partial derivatives. And right, let's go up to this part now that we had skipped before. This is a bit conceptual. Alright, so the partial derivative fx of x0, y0 is found by taking the derivative of f of xy with respect to x, treating y as a constant. Now, the representation is just like calculus 1. It represents the instantaneous change in f per unit increase every time the x increases by 1. Let's imagine how we might visualize the relationship between h, t, and I. or TH and I, the temperature, humidity, and then the heat index. They will become the X, Y, and Z respectively. I is a function of T and H. I is the output variable, T and H are the input variables. This gives you a surface. Consider this point, 9670 is on the floor. So if this is a physical classroom, the XY plane, the floor is the domain. And then you go 125 units straight up from that point. And there's your point on the surface. Okay. The domain of this surface is the XY plane. We stand on the point 9670 in the XY plane, and the surface is directly above us at a height of 125. Remember again, the analogy I like to use for surfaces is we pile dirt on the floor to the prescribed heights according to this function. And then we put a tarp on that, and that tarp is the surface. Okay, but we're standing on the floor, and 125 feet above us is the point. Okay. Now, as we move one unit in the positive x direction, now you got to know what your x-axis, your y-axis, and your z-axis. So visualize this. Suppose we're in the physical classroom, and you're all standing, you're sitting in your chairs, and I'm standing at the board. Okay. Now, I turn around so I'm facing the same direction that you all at the board, and then to my left and way down in the corner of the room, that's the origin. The x-axis emanates from that point along the floor but goes out towards the class. The y-axis goes underneath the chalkboard. The z-axis goes straight up. Okay. So I'm standing at the point 9670 in the XY plane, in the classroom. Okay. From that point, I move one unit in the positive x direction. So I'm moving parallel to the x-axis, one unit. Now, the surface increases by a height of, now if I did, both sides of it, it would increase by a height of 3.75. But moving from, now if I went back to the point 9670, but moving in the positive y-axis direction, so moving in that direction, that increases the height directly above me of the surface by only 0.9. Actually, these estimates are based upon moving along what we call the tangent plane of the surface at the point 96, 70, 125. So, remember in Calculus 1, there were tangent lines for a function. That gets replaced now by a tangent plane. There is, on that tarp that's sitting up there, at a particular point, there's only going to be one plane that's going to be tangent to that surface that'll just nick that point. Okay. And on that tangent plane, these are the things that are going to be happening. If you moved one unit in the positive x direction, your height goes up by 3.75. One unit in the positive y direction on the domain, on the floor, and then you look straight up, the tangent plane would have increased in height 0.9 feet. Okay. So the following problems work on visualizing the tangent plane. All right. So there's a lot of abstraction in that. And are we ready to go to these problems? Give me a tiny bit of feedback to let me know. Did what I just said with all this, were you able to follow this? or did it mostly confuse you?
It's basically what you said earlier.
Okay, all right, so it's making sense to you, Cameron, that's good. All right, makes sense to Rowan. Alright. Not quite yet for Hisu. Okay. Well, let's try it with these and then see. Okay. Use a sheet of paper or a notebook as your tangent plane. Now, this activity we're going to do now, I usually do this, you know, in the physical classroom. It's the first time I'm doing this online, so it's going to be a little more challenging. Okay, the origin will be the front left bottom of the corner of the classroom while facing toward the professor who's at the front of the room. The y-axis will be the intersection of the floor and the front wall. Z-axis vertical, remaining axis moving from the for all toward the students, the x-axis. I want you to tilt your paper or notebook such that f of x is equal to 0 and f of y is equal to 1. So, while you're trying to figure out what that means, and tilting a piece of paper so that those conditions are true, I'm going to get my camera ready. And unfortunately there'll be a little bit of buzzing here. Got the document camera. Get that. Going. Okay. So this is my Wacom tablet. This is what I use to write on the screen. And you see it's very thin. It's acting as a plane for me. So you might have a sheet of paper, but I have this. And now we have to determine what is the x-axis and what is the y-axis on here. And let's just take this sheet of paper here and let's just make it kind of ordinary here. Here's my x. It's like good old two-space. Here's my y. And that's on the plane. Now, I want to make things such that my fx is 0. To make my fx 0, I have to have this such that when I move one unit to the right over here, I don't increase in height. My increase in height is 0. So I'm going to place this line right here. So now I can rotate this in any direction that I want. And all the time that I'm rotating it, I still have fx equals 0. But I'm totally free to rotate this any way I want, as long as I keep that bottom edge on the paper. So, given that that's my only mobility allowed now, I want to set things up so my f of y is 1. Partial of f with respect to y is 1. So that means that when I move one unit in the y direction from here to here, my height has to increase by 1. So I tilt this at a 45-degree angle over here. So then when I move one unit in this direction, I go up 1. Every time I go over 1, I go up 1. Now, I know the visuals were a little bit different because it's on this camera. Give me a little feedback. Does that make sense? All right. And can I get a little more feedback than just one person? All right. And kind of. Okay. Let's try it again. Fx is now 3, Fy is 1. Tilt your piece of paper or book or whatever it is you're playing so that it meets conditions in number 2. All right, let me go there. Camera. Now, every time I move 1 to the right here, my height has to increase by 3. So, I can't have this. I can't have this just flat on this now. I have to be tilting it steeper and steeper and steeper, quite steep in fact. So that when I move 1 towards the positive x direction, the height of this thing increases by 3. Now this line from along here to here has got to stay. But I can swivel this thing around. I can swivel this, but as I got to keep this thing vertical in this sense. This line is still staying the same, but I have freedom of rotation while this line is still fixed. And now, we come back here. I've got the fx being 3, and the fy is 1. So, all the ways I can rotate this, you see, if I kept it just like this, let's tilt it a tiny bit like this. So this is still the way it was. This line is still the way it was. But I tilt it just like this. Now I move 1 in the y direction, and I'm going to be really steep, super increasing. So I want to, now I have room to wiggle this. So fx is pretty steep, but you rotate this around so that as I move in the y direction, I'm finally oriented so that it's kind of 1 in the y direction, and it's kind of a 45-degree angle-ish up, like that. Now if I, go other things, it's too steep. It's hard to get it really shallow with the x being 3. How would I get the y being really... Oh, I could kind of bring this edge way down here. Yeah, so it's almost flat on the paper, this line, this little bottom line right here. But that would be really shallow. I want it to be a little more steep than that. Alright, so this is just trying to work on your intuition for these things. And let's go this one over here. Let me give you a quick 30 seconds. Fx is -2, Fy is 1. See if you can tilt your paper. Okay, I'm going to go here. So here the fx is 0. If I lay this down, if I lift the right end up, positive. And as I move to the right, I get steeper and steeper. And but if I go the other edge up, I have it negative, and I want to be moving in the y direction. So as I move in the y direction, I am going up by a 45-degree angle, like this. And so x, moving toward the x, I go down, move towards the y, I go up. And let's do the very last one. Fx is 0, Fy is 5, tilt your paper. So Fx is 0, put this edge flat, Fy being very steep, and just tilt it a little bit like this. Move one in the y direction, I go way up and very steep like that. But moving parallel to the x-axis, I'd always stay in the same height. Alright, and the homework is 2 sections. 15.2, 15.3. Now the concepts in 15.3 are the more difficult part. The actual homework problems go pretty quick and easy. Once you get used to this, treating the other one as a constant, they'll go pretty darn quick. And there aren't very many problems in the 15.2 section. And any questions? All right, let's stop here, and y'all have a great evening.
Thank you.
Thank you. Good night, everyone.
You're welcome. Good night, everybody.
Thank you.
Thank you.